rest of us already got to see all the answers. I'm going to go quickly. Anybody who was not in class checking homework with us, go ahead and pause at the ones that you need. There's 4 and 6. Here's number 10, number 26, 44, 66, sorry, 60, and 62. Is that the last even, guys? All right, anything else we need some further clarification on besides number 23 that I already have ready? Any evens? Going once. Yeah, 10. Anything else? Jaden? 67? Oh, the odd, okay. Let's go ahead and do 23 first because that was the first odd that you guys had ready from collaborating with your groups. Someone tell me why one of your classmates wouldn't have liked 23. I know right away. Why? Fraction. Ah! Is fraction really a big deal? I don't know. What would I have done? I think I would have multiplied everything by 6. Remember me? I don't like fractions. Remember complex fractions? I get rid of them. So I don't know. If I were you, I would have just gone ahead. And I know it's kind of an elimination you do. But I think I would have just gone for multiplying by. Because then, is this a good thing? If 0 equals negative 45? Okay, forget that. Impossible, no solutions. Impossible, no solutions. But if you had done substitution, someone who did substitution like you were supposed to, I'm very, very proud of you. What did you solve for? First x, first y, second x, second y? Second x? Okay. So then the second x, if you had solved, you would have had x is equal to divide by a negative, so it would have been negative 5, 6y. Plus 7. Good. Would have plugged that into the original one. And when you plugged it in, you would have multiplied that quantity by 6. And I think you would have had a false statement. Well, you should have had a false statement also. Because negative 5y, because that 6 is going to cancel, plus 5y is still going to cancel, right? Is that still false? So either way, no solution. We're going to talk about today, technically we'll call that an inconsistent system in the sense of no solution is possible, no intersections exist. Let's go back to number 10 really quickly just because we're right here. Robbie, was that you? Number 10, was that your question? Oh, that was yours, Gavin. Thank you, thank you, thank you. What are the directions, Gavin? Just solve? So looking at the graph, I can see 3 intersections. Like graphically, that's pretty straightforward. Well, graphically, is that exactly at negative 2 and positive 2? Doesn't quite look like it. I mean, this one's pretty straightforward. I think I see the 0, 2 pretty clearly, but the other ones are a little bit messier. This was the one with the really nasty answers, right? Help me out. What did you guys solve for, x or y? First y. I think that's what I would have done too. Because if you solve for the first y, pretty quickly you're able to get an expression that you can plug in. And with that x cubed, I don't think I want to go solving for x and having to cube something. That doesn't sound fun to me. Remember, we're not computers. We can be creative. So we end up just with x cubed minus 2 plus 2 minus 3x equals 0. Nice thing is your 2's cancel. I'm going to do a little factoring, right? Don't I get x equals 0 and then plus or minus root 3? You could factor it x plus root 3, x minus root 3, or you could just add the 3 plus or minus. Yeah. See? Because those are just x's. So then we have to, and this is why you saw in the answer key, we have to go find each of the y's by, remember, back substituting. Yeah, it's not that bad. It was just a little bit messy. Yeah, because it had all the words and all the, right? But all you had to do, I think, is solving for that y was the most basic, and then a quick factoring, setting equal to 0, and solve for each. Got it. Jaden, help me out. It was number 67? Next page. All right, guys, last question. Get your notes out and get them ready to pop back into section 7.2 as soon as we finish this last question. Jaden, this is like that one that we did towards the end of yesterday. So in my head, I'm just going to think of the geometry of it all with my rectangular tract of land. Just going to label length, width. I should say width and length. Remember, when they're telling you each of these pieces of information, they're clues. So we just have to think back to geometry. That perimeter is equal to 2x plus 2y. We just add them all up, add all the sides together. Area. Guys, area of a rectangle, didn't talk about it yesterday, but area though. Length times width, so x times y. And then, Jaden, now we have our system. But I'm just curious for you guys that got this one. Who'd you solve for? First x, first y, second x, second y? Who'd you solve for? First. Just pick one. I'll go for it. X? Okay. So solving for the first x, I would subtract the 2y to the other side. I would divide by 2. That gets me, you guys see that I can divide everything by 2, right? So I'm going to get 22 minus y. What function is this going to end up being, guys? I see a quadratic too. It's going to be 22y moved to the other side, and then negative y squared moved to the other side. So once you distribute your y and move them all to one side, you should end up with the following. And what are we looking for? Factors, yeah? So with our 120 and our 22, I mean, what do you guys find for your factors? 10 and 12. Equals 0. Just like before, when we get multiple solutions, we have to go ahead and plug in and see what's going on. So if we plug in when y is 10, x is going to end up being 12. When y is 12, x is equal to 10. Does it really matter either way? No. So the long story short, we're just going to have a 10 by 12 rectangular track, both measured in kilometers, right? There we go. Does that make sense, kiddo? All right, cool kids. With that, section 7.2. 7.2. Kiddos, here in the second semester, we're going to do more of what we did at the beginning of class today. I just need you guys to be a bit more effective with it. What do I mean, a bit more effective? What did I ask you to do at the beginning of class after writing down the homework of the non-posted Google Classroom assignment? Go over, I didn't say the evens. Okay, a few of you guys were confused by my saying the odds. Why did I ask you in your groups to go over the odds? What happened? Well, yeah, but why would I not have you guys go over the evens? Because couldn't people be stuck on the evens? But does anyone truly know the answers to the evens yet? Okay, so the odds, you tried it last night, you should have. You checked it in the back of the book, you knew what the answer was supposed to be, and you were able to access Calc Chat. So do you think if someone has a question on the odd, it's a pretty serious question? Does that make sense? Like, it's a pretty serious, they got stuck and they knew the answer. They were able to see a variation of the solution. So when homeworks are due, before we go into grading the evens, I'm going to have you guys in groups collaborate on the odds because those questions are serious. Does that make sense? But I need a couple things. I need those of you guys who are like, I don't think I have any questions on the odds, to legitimately reach out to your group and check on them. Check in with them and make them answer you. Don't just like awkward silence. Okay, I guess I'll just turn around and not say anything anymore. But actually be like, no, guys, get out your homework. Okay, let's see. Is there anything going on in the odds? And then those of you guys with questions on the odds, what do I need you to do? Ask. But hold on. How do you know what your questions are when you come into class? Quick review from the beginning of the year. Yeah, you should have already done homework last night and already checked the odds in the back to see which ones were right or wrong. And you have little question marks by any of the ones you got stuck on before you ever post on Google Classroom. Are we tracking? All right. It'll make things a bit more efficient. Where did we leave off yesterday? Elimination, we saw that even these two examples that we did in section 7.1 could have been done with elimination. But ultimately, there was still some math that we had to do. We still would have had to go to factoring. It still would have been a bit nasty. But elimination might have gotten us there a little bit quicker. We saw even if they don't totally match up, you can still sometimes eliminate at least some sort of quantity. But you might still need to eventually go to your graphing calculator, whether by graphing both and finding the intersection, removing it all to one side and using the 0. So that was kind of the very last thing. And it's actually really good just skill with your calculator, cool kids, getting ready for calculus and the AP calculus exam. A skill with your calculator is knowing how to solve equations that are impossible by hand, like this one. Impossible to solve by hand. Exactly. So there are two different ways of doing it. One way is with that intersect feature. Remind me really quickly, where's the intersect feature in your calculator? Second, trace. What do you need to have in your y equals? How many equations? At least 2. You can't do intersection if it's only 1, right? So either using the intersect feature with these 2, there's your y1 and your y2, or using the 0. Where's the 0 feature? Also second trace. But how many graphs do you need for the 0 feature? Just 1, and you're looking for his x-intercepts, right? So both ways will should get you to the exact same solutions, whether you're intersecting or whether you're finding the 0. It's 2 different variations to the exact same thing. Can anybody think of when 0 would be better than intersect? Now pause. When would intersect be better? If you only have 2 graphs, don't you just have to do like enter, enter, enter? Like first curve, second curve, guess, who cares? Enter, 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 no scrolling back and forth. This one's kind of nice to put in your calculator. Enter, enter, enter. Hey, there's an intersection. Go over a little bit. Enter, enter, enter. There's another intersection. Isn't 0 a little bit annoying at least? You have to get to the left, you have to get to the right, and then it has to find it, guess in between. But why would 0 be better? Maybe only looking for x values, which is, well, for either one though, there should only be one unknown. Sadly, if there's 2 unknowns, we're in some trouble. Think about word problems. How big do the numbers get in word problems? Especially in like finances and stuff. Pretty big. Ooh, how big is your window right now, almost everybody? 10 by 10. What if your intersection is 5,280 and 37? You'd have to go find it. Are you going to see the intersection on a 10 by 10? So what's the dilemma with intersect? You have to change your x and your y to go figure out where it's intersecting. What's nice about the 0 feature? You might have to change your x's, but where is the y always going to be? 0 on the axis. So this is kind of looking forward to AP Calculus. I know. But we're trying to get better at our calculator, better at the basics, so that when you learn the calculus, you don't have to relearn all the basics. Intersections are great unless it's way off in Timbuktu. Forget it. Do the 0. You know it's on the the x-axis. Just keep changing your x-min, x-max until you see it hit the axis. And there it is. So you don't have to go looking with x's and y's and zooming out, zooming out, zooming out, and possibly getting kind of lost in your window. Okay, we didn't get to here yesterday, did we? This might seem a little silly because you guys, once again, are like, elimination, I know it. I've done it since Algebra 1. Yeah, but didn't we see in section 7.1 even substitution got a little bit hard? True? Okay, so elimination, do you think it might get a little nasty? And beyond that, do you remember how I said chapter 7, what are we trying to think like to some degree? Programmers, right? Thinking about how a computer has to think, or has to be given information to be able to process. So to that end, we have to think about, okay, what's legal and what's not? Not just what would pop into my mind to do, but what's legal and what's not. Well, okay, here's what's legal with elimination. Here's getting a little bit more in depth in the process. P.S. really quickly, whose notes? Somebody left it. I'm pretty sure it was from Honors Pre-Cal. Ah, gracias. There you go. I don't know if you need it still, but yeah, I figured. Fly into a headwind. A tailwind, Kim, is helping you and making you go faster. A headwind is against you and so slowing you down. Yeah. Okay, what's legal in elimination? You can change any two equations. If you have a first equation, second equation, whatever, you can say, never mind, you're the first and you're the second. You can change the order of any two equations. You can multiply entire equations by a non-zero constant. If you multiply by 0, why is that kind of counterproductive, I should say? 0 equals 0, everything's gone. Oh, well. And you can add a multiple of one equation to any other equation in the system. Those are the legal steps. Technically, if you really want to know where we're really headed to how the calculator has been programmed to solve with matrices. If you're really curious as to where this part is headed, we're not going to get there today by any means, but we are headed towards how is your calculator programmed to do matrices. Because matrices say, give me a 3 by 3, give me a 4 by 4, give me a 5 by 5, give me a 6 equations with 6 unknowns, and I'll solve it for you. It's pretty cool. Because by hand, 6 equations, 6 unknowns, that just sounds awful, right? So how is the calculator programmed to be able to solve with matrices? Anyway, that's where we're eventually heading. But right here, this is what's legal. We can interchange equations, we can multiply whole equations by non-zero constants, we can add a multiple of one to another. Okay. But what happens? Well, what are some weird things that happen? You guys have seen the word equivalent before. Come on, you've had to. What's equivalent mean? Something is equivalent. Almost the same, basically the same. And in math, we'll say the same. Can I give you an example of the same? Why are those the same? Yeah. But how could you know that? So aren't you kind of, in some way, shapes, or form, aren't you kind of doing elimination when you do that? So when you're thinking about, oh, hey, that's a multiple of, you're really multiplying it by 3, or you could be multiplying it by -3 and saying, oh, it's the same. So what happens if you would have done elimination? What would you have gotten? 0 equals 0. Is that the only way of having an equivalent system? Not necessarily, but for right now, let's go ahead and just put it this way. One equation is a multiple of the other. And guys, it isn't like vectors where we have to worry about direction and one's the negative and the other one's the positive. We don't have to worry about that per se. That's not a big deal. But yeah, if one equation is a multiple of the other, then we're also always going to say that the system is equivalent. And we're going to go ahead and say 0 equals 0 is a huge indicator of that because everything just canceled away. Okay? Consistent. Consistent. If you guys want to think about equivalent, that would be the old school Algebra 1 example if we're only dealing with linear functions. When it's the exact same line. The answer would be all solutions as far as, right, the intersections if one line is the same as another. Consistent. Which one sounds better? Yeah, exactly. Right? There are possible solutions. And I'm going to say finitely many. Ooh, finitely many. That sounds snazzy. What does that mean? Only a certain number. Not like a plus 2 pi n. I know, I just went to... Not an infinite amount of solutions. Equivalent is an infinite amount, but not just an infinite amount, every single point is shared. Every single point is shared. That's equivalent. Consistent, there are possible solutions, there are intersections, and there are finitely many. So, quick example, like the one that you guys saw in homework. Oh, but can I remember it? It's the one we just did. Do we still have it? Nope, not that one. Just kidding. Let's say select. Corresponding to, aka matching up with, right? Select y values. You could say finitely many, I was just lazy and didn't want to write it. So just select a number of x values that correspond to a select number of y values. Why am I not just going to say one solution? Because we're way beyond the linear. How many ways can lines intersect? I know, all, one, none, right? But if you have quadratics, if you have circles, if you have trigonometric functions, if you have e to the x, you could have more than one. So we're just going to say, okay, there's finitely many, could be 1 or 5 or 10, but there's not like an infinite number, and it's not all. Inconsistent, what does that sound like? No solutions, good. No solutions, that one's pretty easy. Because your system will literally end in a false statement. 0 equals 5. Nope. Now wait, pause. Could you have made a mistake somewhere? Of course. But, no, there are going to be inconsistent systems where there are no solutions, no intersections, and it's not just between lines. It could be parallel lines, but as we've been talking about, it could also be a parabola that's down here and an e to the x that's up there, and they'll never intersect. These are words you guys would have seen in Algebra 1 for sure. But just quick reminders of what they mean and how you get them. And the fact that we're not just dealing with lines anymore. Not in Kansas anymore. Ready, set? So applications. Where does this section end? Word problems. Are you going to have some? Probably. How do you know a system is necessary in general? Well, usually you have more than one unknown, x, y, z. And usually, not usually, always, for a system, there's 2 or more equations or conditions that need to be satisfied. So like Jaden's question with the rectangle problem, they told me about perimeter and they told me about area. It's a system. In finance, breaking even, you're thinking about profit and you're thinking about cost. It's a system. In that whole trying to figure out which way you'll get paid more, you were thinking about either straight commission or salary and commission. It's a system. So if there's 2 or more equations, 2 or more conditions that need to be satisfied, it's going to be a system. And as you're thinking about a system, 2 or more equations, well, I'm sure you have 2 or more unknowns. So as with any word problem, we're going to try to analyze it and try to summarize what we've been given, what we need to find. But part of that is going to be probably more than one equation, more than one condition that we'll have to work with. You guys remember from algebra, though. How many equations do you need to solve for 2 unknowns? 2. Unless it's a complex number, that's a special case. How many equations for 3 unknowns? How about 4 unknowns? How about 5 unknowns? All right, this will be fun. So what if we have, ironic, Kim was talking about a headwind a second ago. What if you have an airplane flying into a headwind? Oh no. What if you have an airplane flying into a headwind, traveling a 2,000-mile distance between Chicopee, Massachusetts and Salt Lake City, Utah in 4 hours and 24 minutes? Do we know how fast said airplane is going if you guys quickly read through reading comprehension the rest of the problem? How fast is the plane going? No clue. How fast is the wind? No clue. All right, well. What's going to happen as you're flying there? The plane is trying and the wind is taking away some of its energy, right? So the plane is trying, the wind is taking away. How far are you flying? 2,000 miles. Do you guys remember this good old-fashioned formula that distance equals rate times time? So if we're talking about the speeds of the airplane, what quantity is that? And the speeds of the wind? The rate, right? Rate times time equals distance. How long did it take the airplane flying into the headwind to get from Chicopee, Massachusetts to Salt Lake City? Oh, that's gross. Hold on. Let's go ahead and do some dimensional analysis just to get it all into minutes. Yeah, sound good? Or we could do 4 hours. You want to do it in hours? We can. We can do 4 and 24/60. Is that cool? All right. So we'll keep it hours if you want. Fine. 4 and 24/60 of an hour. But what else do they tell us? Because we have two unknowns. That can't be all. On the return flight, the airplane travels this distance. Wait. On the return flight. Assuming everything stays constant, which we know in this world it doesn't, but trying to keep it basic for our purposes to at least get the idea. If the wind is still blowing the exact same way, the plane turns around and is now going the opposite direction, what's the wind doing? Helping. How long did it take? Only 4 hours. And how much distance was covered? We're assuming everything was constant, so 2,000. Oh my goodness, what do we have? A system! And what should you do to solve said system? If I were you, divide by 4 and divide by whatever that is, and then solve your little baby system by maybe adding. Anyway, you guys play with elimination tonight. You have homework section 7.2. Yeah, there might be some word problems, but I think you can do it. All right, cool kids. See you tomorrow. Bye.